Okay, it looks like everyone's in. So welcome everyone to this week's edition of Paleo Perks. We're really excited to have Georgy Falster from Australian National University in Australia. And Georgie's talk will tell us all about new reconstruction reveals natural and forced behaviour of the Pacific Walker circulation over the last 800 years. So the format of today's seminar, if you haven't been to a PaleoPack seminar before or you haven't been for a little while, we have some welcome announcements for the first 5 minutes, which is currently what we're doing now, followed by Georgie's talk, a short moderated Q&A, and then an after talk tea time, which Georgie has very kindly agreed to stay for. We very much encourage you to stay for this as well. Don't forget to send your questions via the chat to the questions at PaleoPerks host, who today is Chris. So a little bit of housekeeping. PaleoPerks values the participation of everyone interested in the paleo sciences. Please remember to abide by our code of conduct during today's seminar. If you somehow found yourself here without having signed this, please take a moment to go to our website and review and sign it and sign up to our mailing list. Please remember to mute yourself for the duration of the talk. You shouldn't be able to unmute yourself, but if you find that you can, please remember not to, so that we can maintain a nice, quiet environment for our speaker. You can ask questions by chatting to the questions at PaleoPerks host or by using the raise hand function. So we'll make sure that you can unmute and ask a question by voice if you would like to. Any technical issues should also go to the questions host. We have closed captions built into our Zoom, and you can use the CC button at the bottom of your screen to show or hide them. If you hide them for you, it will only hide them for your account and not for everyone else. Please remember to nominate all of your outstanding early career friends using the link that will be in the chat very shortly. And we also encourage you to fill out our weekly feedback form for demographic information. This is anonymous, optional, but very much encouraged, and you'll also be able to find this in the chat window very shortly. And now I'm really excited to introduce to you our speaker for this week, Georgy Falster. So Georgie did a bachelor's at the University of Adelaide in Australia, and also did her PhD there as well, followed by a postdoc at Washington University in St. Louis in the US. And she's currently a postdoctoral fellow at the Australian National University in Australia. And with that, I will hand over to Georgie for her talk.
Thank you very much for that lovely introduction. I will just share my screen. You can see the correct screen here, I hope.
Yep, all good.
Excellent. All right, well, thank you very much to the committee for inviting me to give this seminar. And so I'll be talking about the Pacific Walker circulation's behaviour through the past 800 years, which includes, of course, the transition from the pre-industrial to the industrial era. And so just to start things off, what is the Pacific Walker circulation? It's the zonal, which is the east to west component of atmospheric circulation over the equatorial Pacific Ocean. And on interannual timescales, you can think of it as the atmospheric arm of the El Nino Southern Oscillation, although they're not exactly the same thing, particularly on longer timescales. But we can approximate the strength of the Walker circulation using the sea level pressure gradient across the Pacific Ocean, this delta SLP metric, where we have convection and climatological low surface pressure over the Indo-Pacific warm pool, and climatological high pressure where air descends over the Eastern Pacific. And the Walker circulation doesn't always operate at the same strength. So for example, we can have a weaker Walker circulation. That's a flatter sea level pressure gradient. And on interannual timescales, this lower sea level pressure gradient is analogous to El Nino-like atmospheric conditions. And then on the flip side, we can have a stronger Walker circulation or a steeper sea level pressure gradient, which is analogous to La Nina-like atmospheric conditions. And these changes in the strength of the water circulation affect rainfall all over the world. So particularly across Asia and Australia, the Pacific Islands, North and South America, as well as parts of Africa. And so that's what this map is showing, the correlation of the water circulation in terms of that trans-Pacific sea level pressure gradient with rainfall anomalies over land, and I've stippled over areas with a significant correlation. But despite its importance for global rainfall, we actually don't have a great handle on how or even if the water circulation has changed in the industrial era. So that's since humans started adding large amounts of greenhouse gases and aerosols into the atmosphere. Theory and model simulations generally predict that the water circulation should weaken in response to greenhouse gas forcing. So that's a trend to more El Nino-like conditions. But this isn't backed up by our observations of the water circulation over past decades, which generally don't show much in the way of a long-term trend. This is probably in large part because, like ENSO, the water circulation has really large year-to-year variability, which means it's actually difficult to detect a trend within that over the relatively short observational era. But also some recent work, including from our research group, suggests that different anthropogenic forcings actually have opposing effects on the strength of the water circulation, which kind of muddies the waters, especially for predicting what the water circulation will do in the future, and hence rainfall changes in its teleconnected areas. Observational data sets at least agree that the water circulation actually strengthened from the early 90s to the early 2010s, but the jury is still out to a degree on what exactly caused this. The general consensus is that this strengthening was caused either by anthropogenic aerosols or that it was related to the 1991 Pinatubo eruption, and that it can't be explained by natural variability. It's unprecedented. But this is quite a bold claim to make about a 20-year trend when we have at most about 100 years of observational data to work with. Because of course, to properly test claims like this, as well as more generally tease out forced water circulation changes from internal variability, we need a longer record. So long enough that we can start to disentangle the influence of things like greenhouse gas and aerosol forcing, but also compare this with model simulations over longer periods to see if the large-scale changes are similar. Then this in turn will give us a better understanding of what the water circulation might do in the future, and hence potential changes to global rainfall patterns. Okay. And so to do all of that, what we need is a variable that has a close mechanistic relationship with the water circulation and proxy records for that variable that go back long enough in time to be able to assess the influence of external forcings, as well as being able to sort of quantify the nature of water circulation variability on timescales from annual right up to multi-decadal and even centennial. And for that, we turn to water isotopes, which is to say the stable hydrogen and oxygen isotopic composition of precipitation or rainfall and other environmental waters. All right, so as to why water isotopes are the right tool for this particular job, we're actually going to deviate now into some basic water isotope systematics. The upshot of which is that the stable isotopic composition of precipitation contains a lot of information about regional weather and climate, also atmospheric dynamics. It's a very integrative tracer. And so just for a warm-up, you can see that very clearly in this beautiful daily record of precipitation amount and precipitation delta 18 from Malaysia. So on the left is daily rainfall amount at the collection site here, regressed on rainfall across the tropical Pacific. And you can see that it's really a very local signal. The correlations don't extend very far. But on the right, again, is rainfall amount across the tropical Pacific, but now showing the correlation with the isotopic composition of rainfall at that station. And you can see that not only are the local and regional correlations much stronger, but actually that the relationship extends all the way out across the tropical Pacific. And so why? Why is rainfall delta 18 so much better at recording regional precipitation than is local precipitation amount? And so the upshot of this is that sort of rainfall, delta 18, it actually responds to a lot of the processes that occur over the sort of voyage of a parcel of water vapor from its source through to its point of precipitation. And so to show you why exactly this is, I'll zoom through some water isotopes 101, which is that both hydrogen and oxygen have multiple stable isotopes. I'll only talk about oxygen here, but the same applies to hydrogen. And because of the differences in molecular bond energy, water molecules with the heavy isotope, so oxygen 18, will seek out the lower energy phase states. So compared with oxygen 16, they'll condense to liquid from vapor. And we'll also prefer to stay behind in a liquid reservoir when water evaporates. So we call this mass-dependent fractionation. And so we report the ratio of oxygen 16s to 18s in a measured water sample with this quantity, delta 18, which is the ratio of heavy to light oxygens relative to that of the standard. So just to illustrate that, I will use my favorite metaphor, which is cats. So in this case, we have Fluffy here standing in for oxygen 16. Fluffy weighs a total of 16, is a relatively sort of light, svelte and active cat. Then on the other hand, we have Captain Sprinkles, who weighs a majestic 18, is much more chill. He'd rather just, slob around and eat biscuits. So when water evaporates from a reservoir of liquid water with a certain ratio of Fluffy the Captain Sprinkles, as evaporation occurs, the nice light fluffies zoom away into the vapor phase, like in this diagram on the right, whilst Captain Sprinkles just chills out in the liquid phase. And this means that compared with the original delta 18 of the liquid reservoir, the vapor is depleted in oxygen 18, so it has a lower delta 18 value. And the remaining liquid ends up with a higher delta 18. It's become relatively enriched in the heavy isotope because more of the light isotope has gone away into the vapor parcel. Okay. And this mass-dependent fractionation is also temperature-dependent, so we get more fractionation at lower temperatures. So in this example, if it was a bit colder, then maybe the vapor would have a delta 18 of -10 and the remaining liquid a delta 18 of +4. And this also, of course, depends on the delta 18 of the original liquid. Okay, so I hope you can see then the water isotopes can capture and retain actually information from any stage of the water cycle that involves a phase change. So including evaporation from some particular oceanic source, moisture transport and cloud formation, and any other processes that happen as a parcel of moisture evolves, precipitation, as well as any subcloud processes, as well as moisture recycling over land. And because the water circulation affects a lot of these processes in a lot of places, even far beyond the tropical Pacific, it's very reasonable to suspect that there would be a water circulation signal in global rainfall delta 18 variability. Okay, so to test this, I gathered all available rainfall delta 18 observations. So this is mostly from something called the Global Network of Isotopes in Precipitation, GNIP. And then to estimate the dominant spatial and temporal patterns in global rainfall delta 18, I simply found the first principal component of variability and the associated empirical orthogonal function, so the loadings of each of the sites on that PC1. To put that another way, this line plot on the right is our best estimate of how global precipitation delta 018 changes through time from 1982 to 2015. So that's the temporal variability. And for the spatial variability, we can look to the map on the left. Okay. So finally, I compared this with changes in the strength of the Pacific Walker circulation over that same interval. And as it turns out, not only does the Walker circulation explain over half of the variance in our global precipitation delta 18 signal, but actually sort of this precipitation delta 18 is more strongly correlated with the Walker circulation than with ENSO or the Indian Ocean dipole or global temperature or any other globally relevant climate mode you can think of. Okay, so we've established that there's a really strong imprint of the Pacific Walker circulation in global precipitation delta 18 patterns. This is for various reasons that are not surprising. You could read them about them in this paper if you like. But that's great because what we also have is sort of more or less globally distributed proxy records for the stable isotopic composition of surface waters in the past. So in this case, mostly from the ISO2K database of water isotope proxy records through the Common Era. And so the map here shows records from that database that are annually resolved and have data through to the year 2000. So there's the little sort of methodological background in terms of the relevant water isotope systematics. Now I'll just step through the full methodology that I used to reconstruct 800 years of Walker circulation behavior. So I reconstructed at annual resolution, so one observation per year for the past 800 years. As I said, I based the reconstruction on water isotope proxy records, where I leveraged that modern Walker isotope relationship by using water isotope proxy records, mostly from the ISO2K database. I calculated the reconstruction using quite a few different statistical methods, and I also explicitly incorporated the effects of chronological uncertainty. And so actually the reconstruction is an ensemble with just shy of 5,000 realizations of the Walker circulation through the past 800 years. All right, and so without any further ado, here it is. This is the reconstruction ensemble where the colored lines show the medians for each reconstruction method I used. The black lines there are observations, and the little triangles show the timing of major volcanic eruptions. Now, just before we continue on, let's zoom in to have a look at the observational era, so from 1900, where we can compare the reconstruction with observations. And here we can see that the reconstruction ensemble agrees well with that Walker index, the delta SLP, the sea level pressure gradient, calculated from observational products. So the reconstruction medians here are shown in the dashed lines. An instrumental sea level pressure gradient calculated from 3 different observational or reanalysis products is in these solid lines. All right, and so that's very nice because now we can sort of confidently use this reconstruction to check out the Walker response to external forcings. Okay, so firstly, looking at whether there's been any detectable anthropogenic influence on the Walker circulation. And the short answer is sort of. We found that the mean state of the Walker circulation in the industrial era, in the salmon distribution there, is no different to the mean state in the pre-industrial, in the teal. The same goes for trends. There's been no detectable change in the overall strength of the Walker circulation. Now, I'll stress at this point that what I'm not saying is that anthropogenic climate change has not had any effect on the Walker circulation. Actually, in this paper here, I argue that this lack of a significant mean state change could be down to at least two things. First, the large natural, just sort of year-to-year variability, which means it's going to take quite a large mean state change to show up. But second is that recent research from various groups suggests that different anthropogenic climate changes actually sort of push the Walker circulation in different directions. So, for example, whilst the thermodynamic effect of global warming might drive a weaker Walker circulation, both the associated AMOC slowdown and also anthropogenic aerosol emissions both drive a stronger Walker circulation. So it's possible that at the moment we're just in this sort of transient state where the various influences are cancelling out. This is, of course, a question for climate models. Our group's working on that at the moment. That's being led by Callie Flager, who's a grad student with Sam Stevenson at UCSB, looking at the Walker circulation in the CESM Last Millennium Ensemble. But also, one of the places I did see a slight change is actually in the power spectrum. Okay, so just to step through this plot here, I calculated the power spectral density for each of the 5,000 reconstruction ensemble members and extracted significant frequencies. I did that for the pre-industrial and the industrial era. And what I'm showing here is the difference in the proportion of ensemble members with power at each period. And so you can see there's a distinct loss of power at high frequencies, so around 2 to 4 years, with the shift to variability at slightly lower frequencies, around 9 years. And what that means in practical terms is that the Walker circulation seems to be getting sort of more sluggish at switching between states. So maybe taking longer to go from strong to weak and vice versa, or dwelling longer in each state. And for a real world example of this, actually has really important implications for things like compound events. So for one specific example, we have the recent triple La Nina event, which, for example, drove extensive flooding across Australia's eastern seaboard, as well as drought in East Africa, and could have been a symptom of this new Walker circulation behaviour, and therefore something that we might expect more of in the future. Right, so that's how I use my reconstruction of the Walker circulation's response to assess the Walker circulation's response to anthropogenic forcing, or in other words, to assess how Walker circulation behavior has changed since humanity started making really large-scale changes to the global climate system. And this change in the year-to-year behavior of the Walker circulation is particularly interesting because it's not something that we've seen in climate model analyses. So it really highlights the ongoing importance of empirically based analyses, even in this sort of current era of science where models are quite often the tool of choice for assessing tropical Pacific changes. All right, so on that note, let's have a look at how the Walker circulation responds to volcanic eruptions now. So again, we're using the power of the ensemble to get a robust estimate, in this case using something called a superposed epoch analysis. Okay. So to do this, we take one of those 5,000 reconstruction ensemble members and a reconstruction of the years of major volcanic eruptions that overlap the reconstruction. I snipped out a 10-year chunk surrounding each eruption, so a few years prior and 6 years after, and then composited all of those chunks into a single 10-year time series. And what that gives us is the average Walker circulation response to volcanic eruptions in this ensemble member. And finally, I tested whether any changes in the strength of the Walker circulation after eruptions are significant compared with the null hypothesis that's designed specifically for this analysis. And the point of this being that if there's any consistent Walker response to volcanic forcing, it will be concentrated in this composite. Now you can see that for this particular ensemble member, there's not a consistent response to volcanic eruptions. The variabilities have mostly just cancelled out to give more or less a flat line. But of course, I've repeated this for all 5,000 ensemble members and report the proportion of ensemble members that have any sort of significant post-eruption response. Okay, and so after all of that, what I found is that the volcanic influence on the Walker circulation is quite clear, with a distinct El Nino-like weakening of the Walker circulation after large volcanic eruptions. So this plot here shows the proportion of ensemble members with a significant positive or negative response to volcanic eruptions. And with a bit of wiggle room for the chronological uncertainty, the response lasts maybe 1 to 3 years in total. There's a lot of nuance to this, which we can talk about if you like. But also this is particularly interesting because sea surface temperature proxies, like corals, for example, generally haven't shown a strong response in a sea surface temperature anomaly sense. And similarly, the ENSO response in climate models is not quite this strong. So this is that same analysis performed on outputs from climate models that have simulations of the past millennium, the top row being for the Walker circulation and the bottom row for sea surface temperature anomalies in the Nino 3.4 region. The columns just show different numbers of eruptions. And it's subtle, it's kind of hard to see, but the response is slightly more coherent for the atmospheric anomalies than for the sea surface temperature anomalies. All right, and finally, thinking back to that recent strengthening that I talked about all the way back at the start of this talk, now we can see how that looks in the context of the past 800 years. So here I'm showing the full possible distribution of 20-year trends in the Walker circulation over the past 800 years. And here in red is the magnitude of that recent observed trend. So you can see that it's in the upper tail of the distribution, but it is not unprecedented. So going back to the proposed explanations for this trend, we did some extra testing, which you could ask me about in a moment if you're interested. But we determined that this is very likely not related to the Pinatubo eruption, leaving anthropogenic aerosols as the only likely external driver of this 20-year strengthening trend. But we've also shown that in fact this trend, although unlikely, could have arisen just due to internal decadal variability. It's actually not unprecedented. All right, so that's a summary of my research from the past few years into the long-term dynamics of the tropical Pacific, where I found fairly clear evidence of a volcanic influence of the Pacific on the Pacific Walker circulation. The anthropogenic influence is less clear, although I think that this spectral shift is really interesting and warrants more investigation. And that's certainly not to say that with future increases in atmospheric carbon dioxide, that a significant weakening might not still emerge. Okay, so that's some science. I actually thought I'd finish this seminar up with something slightly different, which is a summary of all of that in the form of a poem. Okay, so this is actually published in the the second to most recent issue now of the amazing science poetry journal Consilience. They've just got a new issue out yesterday, I think. But I learned about this at AGU a few years ago. They're very welcoming of non-poets like myself, and I would strongly consider any of you or people who are watching on YouTube to have a go at summarizing some of your research in verse. If nothing else, it really helps you to think about your work in different ways. Okay, so then to summarize my work, In western seas at low degrees, converging breeze lifts air with ease. The ocean's warm, so water's drawn to clouds that form convective storms. That air flows east aloft, at least until the temperature's decreased. Then cool and dry falls from the sky to make a zone where pressure's high. And next, this air, it doesn't rest, it turns around and heads back west, closing a ring of air that spins around and brings some different things. If it spins slow, that's weaker flow of air, and so Earth's rain clouds go to different spots. So wet or hot depends a lot on slow or not. Of course, the opposite is true. A faster spin moves rain clouds too. And so you see this air ring's key for knowing where Earth's rain could be. But this ring of air, it doesn't care. It makes me swear and pull my hair. Earth's getting hot, so many watts, but will this thing respond or not? Will it get weaker or get strong? We'll only know as time goes on. There's just no trend. Well, it depends, in fact, on where you put your ends. But stats says no, that's just brought woe so far. And so I've had a go, looked back in time, 800 years, and it appears an answer nears. There's been no change in trend or range. The means maintained. So that explains conflicting signs from shorter times where lines showed increase and declines. But a curiosity is that recently the frequency of ring speed change has changed. It's rearranged itself, and that we can't explain. But there's more here that we saw that helps us guess at what's in store. Here's three main things that drive this ring, so we begin to see within our air ring's heart, and hence we start to tease the forcings apart. Volcanoes flash, releasing ash that spreads and makes a climate splash. Earth shifts a gear just for a year or two until the skies are clear. And with that shift, a sudden drift in places where air's sunk or lift. The ring first slows and then speed grows and then returns to normal flow. And so this quick volcanic shift, it's more a blip than actual drift. But it might be that sky debris in certain spots gives our ring speed. And with that dust gone from the sky, then global heat won't have to vie with forces driving faster spin, such that its influence will win. Then global heat might have us beat because it could make the air ring weak. And there's no doubt, I've shown throughout, this ring's got clout moving clouds about, which means the places where it rains are going to change and cause some pain. Okay, so there's a little summary of my work, and I am happy to take questions, comments, and so forth.
Awesome. Thank you so much. That was a great term.
It started as a COVID project.
Awesome. Just a quick reminder to the audience, you can send in your questions via the chat to the questions at PaleoPlex host, or raise your hand and we will unmute you so you're able to ask your questions by voice. So we've had one question in ready, which I will paste in the chat for you. And this question asks, how did you account for the uncertainties in the chronology? Are there any program/open source codes to reconstruct paleoclimate data?
Yeah, excellent question. The short answer, wait, can you still see my slides even though I've
Yes.
Yeah, excellent. Yeah, I'm just gonna sit on that. There we go. Yes, it's all oh yeah, for a start, all the code that I used in my paper, I think is open source, or if there are bits and pieces in there that are confusing, you can ask. So this was all based, I did the reconstruction using the ISO 2K database, which is in something called the lipid format, which I can, if you can you see my Google Chrome? Yeah, so there's something called the Lipidverse, which hosts various databases, including ISO2K. Now, lipid formats are the sort of the state of the art sort of paleoclimate data format. And they contain a huge amount of information. So there's one lipid file per paleoclimate record, essentially, and it contains the squiggle, the data, but also things like all the metadata associated with that record, information about how to interpret it, how the data were acquired, the specific mass spectrometer, heaps and heaps of information. And also, and this is the key point, information about how the chronology was developed. So for things like lake sediment records, that might be actually the primary radiometric ages, like radiocarbon dates for speleothems, the uranium thorium dates. But then in the case of records like trees and ice cores over these time periods, we actually just apply a sort of it's called a banded age model, where chronological uncertainty just increases at a steady rate back through time. So in this case, at a rate of an uncertainty of 1 year of uncertainty per 100 years of record. And so let's see. And so to account for that, I made essentially for every record, I put the data on 200 different possible realizations of the age depth model. And then I perform the reconstructions many, many times. In each case, pulling from, different members of that ensemble of possible age depth models for that record. So I did all of that in R using tools that have been developed by the Lipidverse team, which are all open source. That's Nick McKay, Juliana Bourget, Deborah Kaider, that group. You can ask me for more information on that if you like, if that's, yeah.
Great, thank you. We have had one question in the chat, which asks, forgive me if I missed this, but is the Walker circulation response to volcanoes dependent on the location of the eruption?
That's an excellent question. You didn't miss it because I didn't go through it. So for a bit of background for anyone who hasn't looked into this, in climate models, it's fairly well, okay, very much depending on the model because there's quite a lot of range in this. But in CESM, for example, which is often used to look into this question, there is generally a stronger response, I think, to volcanoes in the tropics, I think. I forget exactly what it is. In the reconstruction, that was not the case. So yes, I did look into this as much as I could. I mean, we're sort of limited by the number of eruptions in the number of sort of splits we can do, because at a certain point you only have 2 eruptions in a certain latitude window or whatever, which is not really enough to assess a robust response. But within the frames of the degree to which we could do that, no, we didn't see any influence of eruption or volcano location on the response. It's possible, of course, that there is, but it's just overshadowed by all of the other sort of things that are in the mix here. For example, eruption time of year, eruption magnitude, eruption chemistry, as well as a few things like the chronological uncertainty actually makes it harder to detect a significant response. So yeah, I think the only way forward with that really is further down the track to produce a longer reconstruction so that we can encompass more eruptions and do more robust statistics on that sort of but that will require a lot more paleoclimate records, unfortunately. It's a great question.
Thank you. There was a follow-up that came as well, which asks what the impacts of the Nova Rupta eruption was on the Pacific Walker circulation.
Yeah, I am embarrassed to say, I'm sorry, I'm not. Was this a recent eruption? It's not immediately springing to mind to me what the Nova Rupta eruption is. let's see, sorry, I'm so if this was if this was a recent eruption, then I mean, I only know what is, yeah, that's sort of, oh, let's see. 1912. Yes, yes, yes. Right. I think that the something about that eruption meant that it's what do you call it? Like the degree to which it affected the climate system was not as big as, for example, Pinatubo and Agung, and sort of the big three of the 20th century. So I think, yes, as far as I know, I'm fairly confident that this specific eruption did not have a detectable influence on the tropical Pacific. For whatever reason, I'd be happy to look into it. But I think, yeah. I wonder if that one might have been in here actually. But yeah, I think that in sort of in isolation, because it's tricky looking into the climate system response to individual eruptions, right? That's why we sort of aggregate to try to get an average response. But for single eruptions, there's so many other things going on. So for example, in the case of this one, I'm not sure what time of year it was, or the sort of magma chemistry. Obviously it's quite high latitude, but yeah.
Great, thank you. We have another question, which comes from Sender. And Sender asks, why are the correlation values much more spread out in the Pacific Ocean and more clustered around Australia and South Asia in the regional precipitation and Delta 80 correlation plot?
Is that's this one, I assume? So why they're much more spread out in the Pacific Ocean and clustered around Australia and South Asia. Okay, I'm going to talk about this, and if this isn't the correct plot to be talking about, then please pop your hand up quickly and stop me. So this is just, what is it, 25 north to 15 south, so Australia doesn't quite make it. You can see the collection site is marked by this red cross. So there are correlations nearby that are particularly strong. But I think the reason that they're so spread out across the Pacific is because this is capturing information about all the processes that sort of bring rain, not just the processes that cause local rainfall, but all the processes that result in moisture being sort of transported to and precipitated at this location. So that's sort of monsoon dynamics, as well as various other things that actually have sort of close relationships across all of the equatorial Pacific. So, what the processes that are causing it to rain over Malaysia are associated with the processes that are causing it to rain over a lot of the equatorial Pacific Ocean. So, things like, like sort of where the moisture is coming from, where it's been transported from, the sort of energetic seasonality and so forth. And that's why they spread out so much. Whereas with rainfall amount, I guess there's sort of less information in rainfall amount. It's really just, I mean, there's a bit of that alias din, but the ways in which local rainfall amount correlates with regional rainfall amount is it's a little murkier. It relies on sort of a more complicated suite of processes. Yeah, this paper is, I suggest reading this paper. It's really, it gets into it very nicely. The short answer is the power of water isotopes, which sort of combine a huge amount of information into a single variable, and including information about rainfall amount in this specific location. Yeah.
Nice, thank you. We have another question, which asks, and what do you see as the next steps for this work?
A great question. So there's a couple of avenues that we're pursuing. So one of these very much is figuring out why we're seeing this shift to lower frequency variability. That's really interesting. It's really curious. It's a feature of the climate system that had not previously been identified. I mean, the difficult thing here is that it doesn't show up in climate models, which makes it quite hard to diagnose. But definitely figuring out why we're seeing this shift to lower frequency variability, that's one quite important next step. Another is that, of course, this is what we call a statistical reconstruction. So the reconstruction is just based on statistical relationships between the target variable, so the Walker circulation, and this variable with a mechanistic relationship to that, which is global water isotope variability. So, we get a single time series, that's great, it's based on empirical data. But I mean, I think one of the upcoming areas in paleoclimate research is paleoclimate data assimilation, where we sort of quantitatively combine information about, what has happened when, which comes from paleoclimate proxy records, with climate models that have all the sort of physically and dynamically consistent information about what's happening in the full 3D climate system. And so that's really valuable for things like the tropical Pacific, where, there's a lot going on. Now, specifically, there are a couple of existing paleoclimate data assimilation products. So there's the Last Millennium Reanalysis and FIDA. Both of these are annually resolved. They use something called offline assimilation. But I'm supervising a really brilliant student, Jara, at the University of Melbourne, and he's currently developing a sort of a new, very advanced paleoclimate data assimilation scheme, aiming for monthly resolution and assimilating coral data over the past 400 years or so. And so aiming for a really good three-dimensional reconstruction of tropical Pacific variability over the past 400 years or so. And I think that should provide, I mean, it's going to take a long time, but that'll provide some much deeper insights into these changes, as well as things like looking at the strength of coupling between the sea surface temperature anomalies, so like ENSO and the Walker circulation, which I think is another important sort of follow-on avenue from that. So they're the main ones. It's a lot of work.
Great, thank you. So we have one more. Which asks, what is the biological response in terms of organic carbon response across ecosystems in the South Pacific, and how does organic Delta 13 carbon values compare with records of biological responses derived from precipitation, and how is carbon been used as a proxy? Maybe several questions in one.
Yeah, that's a great question. Unfortunately, I will say up front that this is not my area of expertise. So for this reconstruction, we used the oxygen and hydrogen isotopic composition of rainfall, because that is a variable that has a close relationship with the Walker circulation. Because of, the Walker circulation affects rainfall and rainfall teleconnections around a lot of places, and those processes are nicely captured in precipitation delta 018. as far as the biological responses, so I guess what vegetation changes as a result of sort of rainfall changes, or I'm sorry, but I'm not sure of that. I think carbon isotopes, my instinct would be that they would not probably be a great proxy for this particular aspect of the climate system, just because, it's an atmospheric variable. It's related to rainfall amount. If we're looking at a biological response to that through delta 13C, then that's sort of a few steps removed. So yeah, for this, I'm not sure. Of course, delta 13C and in speleothems and so forth provides amazing records of various different aspects of the climate system in different specific places. But for this particular research, no, I'm sorry, I didn't look into it. So yeah, it's many different proxies for many different tasks.
And they all fit together for a nice story.
Mm-hmm. Absolutely.
Nice. So that brings us to the end of the Q&A, and I will take back the screen share from you. Okay, that should work. So thank you very much again to Georgie for such an excellent talk. I know I learned so much about your proxies. And thank you to the audience for joining us this week. Please remember to fill out the weekly feedback form. The link will be in the chat so that we can learn a bit more about who attended today's seminar, and join us next week on April 2nd at 1500 UTC for a talk by Alison Jackable from Middlebury College in the US. And Alison will be talking about deep Pacific carbonate chemistry of the last deglaciation. And up next, we have tea time with Georgie. So this will be an informal conversation about the talk in a relaxed setting. We very much encourage you to stay. And our question of the week this week is: share your favorite research discovery or anecdote or story by you or a colleague. But first, it's time for a break before tea time. Remember to get up, walk around, have a quick drink of water, come back in 2 minutes. And if you have paleo pets with you, please remember to bring them as well, because we like to leave them. We will see you in 2 minutes.